A car moving at a constant acceleration covers the distance between 2 points 60 meters apart in 6 seconds. Its speed as it passes the second point is 15 meters per second. No, but I saw Joe Mama's backpack today. What was its speed as it passed the first point? What is its acceleration, and at what prior distance was the car at rest? Yeah, see, 7,000-year-old vampire was not born yesterday. All right, let's get going. Okay, so 2.60 meters apart. Delta x is 60 meters. Delta t is 6 seconds. Its speed as it passes the second point is 15 meters per second. What was speed at its first point? What was its acceleration? And what was its way back? Like what time? How far? At what prior distance from the first point was the car at rest? So let's go ahead and say it's sort of like a delta x 0. All right. So VI, we're going to solve for VI the same way that we did before. Delta x equals 1/2 VF plus VI multiplied by time. Okay. So we know that it's 60 meters, 1/2 15 plus whatever the VI was multiplied by 6 seconds. Okay. So if we divide both sides by 1/2 of 6 or 3, we end up with 20 meters, or 20 whatever, equals 15 plus VI. Okay. Subtract 15 from both sides. Our initial velocity is 5 meters per second. That's how it. That's how much it changed from the first point to 60 meters later. 15 seconds later, it went from 5 meters per second to 20 meters per second. Now it says what's its acceleration? The easiest way to do that is take our change in velocity and divide it by our change in time. So VF minus VI over delta t, which is 20 minus 5 over our 6 second time interval. So 15 I'm not sure what you mean, Quentin. I feel like all of our questions are pretty straightforward. I feel like you guys look for twists and turns and end up finding twists and turns that aren't really there. So that's I don't know how to teach around that. Okay, they are still going to be word problems though, as opposed to say like they're not just going to be a list of stuff for you to just plug in. So I'm not 100% sure I answered your question, but so our acceleration is 15 divided by 6, or 5/2. Yeah, 2.5 meters per second squared. So that's our acceleration. Okay, let's take a look at it up close so you guys get a chance before I erase it. Okay, I'm going to erase some of this stuff so that we can do the last little bit. At what prior distance from the first point was the car at rest? Okay, so since it was talking about the first point, how far from the first point was it at rest, our initial velocity at that first point, like we just figured out, is, I actually did that one wrong, didn't I? It's 15 plus 5 equals 20. Oh, dang. Alright, I'm sorry. Let me redo a part of it. So I'm having to redo some of it. VF minus VI equals A delta T. It goes from 15 to, it goes from 5 to 15. So it's actually 10. And divide both sides by 6. So so acceleration is actually 10/6. Dang. 10 divided by 6. So 1.66 meters per second squared. Okay. I apologize. That one was my fault. Again, so Quentin, that's not actually a distinction that's worth distinguishing. Again, you're just thinking too hard. So it just is, buddy. Anyway, so that's actually our acceleration. I screwed that up. 5 meters per second, and our acceleration is 1.66 meters per second squared. Okay, and now how far back in the past was our car at rest? But it matters for the ball throwing question. Only sort of, only in name. Again, you're overthinking it. You're overthinking it because when the ball does hit the ground, when it hits the ground, it is traveling at whatever we said it was traveling at. It's not until after it has completed its collision with the ground that it is stopped. It doesn't stop suddenly. It slows very fast to a stopping point at the ground. It doesn't actually stop instantly. So that is just the way we describe it so that you understand it better. But you got to stop overthinking it so much. Anyway, so moving on. We've got all of the stuff we've written down, all the stuff we've calculated so far written down. And now we're trying to figure out at what delta x before the first point is it stopped. Okay? And so let's see if we can't figure out a way to do this. I believe we can use this one. Okay? So in this case, we are imagining that it goes from 0 up to the velocity at the very first point. So from 0 to 5. Okay? From 0 to 5. And so let's go ahead and type that in. 5 squared equals 0 squared plus 2 times our acceleration, which is 1.6 meters per second squared, multiplied by our delta x. Okay? So 0 squared is 0. 25 is 5 squared. And we have 3 1/3 delta x. That's what we've got right now. And then if we divide both sides by 3.3, we have delta x equals 7.5 meters. Okay, and let's go ahead and check and see if that's actually the case. So let's see how long it would take for it to get from 0 up to 5 meters per second. Okay, so I'm off the chart. Okay, so let's see how long it would take to get from 0 up. Why didn't I use 60? I used 60 for the first part, and then for part C down here, at what prior distance from the first point was the car at rest? That is before everything. So that's why I didn't use 60. So we have VF minus VI equals acceleration A delta T. We know our final velocity is this one as it crosses the first point, which is 5, and our initial velocity, which is 0. Our acceleration is 1.6 repeating, multiplied by time. Divide both sides by that 1.6 repeating. And what we have is 3. Our change in time is 3 seconds. So let's see how far it would have gotten in 3 seconds if we knew that from before. So delta x equals 1/2. You know what? I'm going to go ahead and erase some stuff. Let's write that down so I can remember. And that the value we got to begin with is this 7.5.